what we're going to look at is 4140 steel, and we're going to look at the different microstructures and properties that can result when we do different isothermal transformations. Let's look at our first condition that we did. And so this was where we quenched. We quenched from 8 or 850 Celsius, and we quenched down to room temperature down here. Initially, we'll have 100% austenite, and when we quench, we will get martensite. So now we want to look at what results from this. And again, this is real results that we have in our lab. And so I'm going to kind of walk you through what we see. So for the quenched 4140 steel samples, we get a microstructure that looks like this. And so these are two different images taken at different points. But one thing you'll notice is a lot of individual, very small kind of needles or thin lenses almost. This is very indicative and characteristic of martensite. So like I said, it's predominantly martensite, or all these tiny little lenses that we see in these structures, all these little needle thin samples. And again, some of the lighter regions can be austenite that hasn't transformed or retained austenite. So that's what we kind of expect with this microstructure. So we're going to see martensite with some retained austenite. So let's look at what that results on the mechanical properties side. So here's our engineering stress strain curve. We have the elastic portion and the plastic portion. And when we look at 4140 steel that's quenched, this is going to be our most extreme of the samples. So it's going to have the highest hardness. So the Rockwell hardness Rockwell on the C scale is going to give us a value of about 55. This can change depending on what type of quenching we do, water versus oil and so forth. But we tend to get somewhere in the 55 range. This is very hard. So this is typically a value that you'll see on cutlery and other fine knives. They have a very hard, so we can retain a blade or a thin layer. So other things about this, from the engineering stress strain curve, we have a yield strength that's about 1200 and a tensile that's about 2000. And the ductility can vary, but we tend to get an average of about 5% elongation. So it doesn't extend a lot. And so that's what we see with martensite, is it tends to have the extremes. It is the strongest, has the highest values of strength and hardness, but has the lowest value of ductility, meaning it's the most brittle structure we have. So that's actually a problem, because it's in some cases too strong and it can brittly fracture. So that brings us to the last part that I want to show, which is when we do the tensile test, we look at the fracture surfaces and we can draw some conclusions from that as well. And so here, this is the two fracture surfaces that we see. In the middle part, you see this is relatively flat. You actually see some river marks. So this is from the fracture propagating on the center of the region. And then you see a region around the edge. In this case, we have a rectangular cross section. And so the brittle region is this region around the edge. This has an angle sometimes of about 45 or so, but this top surface here is flat. And so this is kind of the brittle region, the middle, and then this is the ductile around the edge. And so you might hear this referred to as like a cup and cone structure. And so you can see that here in a very large very large brittle region, which is flat. So you can kind of see as we progress through these, you're going to see some differences. So let's go to the next one. So up in temperature up to 360. So this was our next one. So just as a recap, we started at 850, we cooled rapidly to 360, and then we held there for about an hour, and we expect to see bainite or lower bainite. So what do we get? What's the results that we see? So here, this is our microstructure. Again, two different images from different groups and different years. And again, you might notice that this structure actually looks very similar to martensite. It can often be mistaken for martensite. And this is just an optical microscope image. But if we were to zoom in, we would hope that we could see those very fine ferrite and cementite layers. So unlike martensite, which is a metastable phase, so it's uniform throughout, bainite is a mixture. So there would be a fine mixture. And so this is kind of difficult to see the differences here, but this is in fact lower bainite. So bainite can be tricky without maybe some electron microscopy to really see the differences. So properties. So this is the engineering stress strain curves for a couple samples at 360. And again, you'll notice the elastic and plastic regions. And when we crunch the numbers, what we see is that the hardness drops a little bit to 42 or so. The yield strength drops to 1100, and the tensile strength drops to 1300. And the ductility jumps up a little bit to around 11 or so. So again, the hardness is going down, the strength is going down, and the ductility is going up. So when we look at these samples, so again, the fracture surfaces of the tensile samples, we see more deformation. So you might actually see that the shape has changed. These were the same exact shape as the previous. So that change in shape means that there's more plasticity, there's more ductility, which you're seeing down here, and there's less flat surface, right? The flat surface part means that there's the flat part of it means more brittle. And so we're seeing less of that here. So we can also see that on this structure. So let's go to the next one. 460. So we did the same thing. We quenched down to 460. We hold there, and it's predicted that we'll have upper bainite. So another form of bainite, but the upper bainite. So let's look at what the results here for this are. So this is our microstructure. You might be able to see a little difference. It's kind of difficult to see. Sometimes you can actually see some ferrite, some of the lighter regions. This might be a little ferrite that's present in the structure, but it's still a very fine structure that's very difficult to tell. It can often look a little bit like martensite, even a little bit like perlite, but you see it's kind of a dark light region here with different phases. That is the ferrite cementite. That's the bainite structure. It's very small. So again, we would really like to see electron microscope images to be able to really see the fine bainite structure. So again, bainites are really tricky to see with an optical microscope, but I'm going to call this upper bainite. So let's look at the structures here. So even though the microstructure might be very similar, let's see about the mechanical properties. So this is the engineering stress strain for a couple samples of 4140 steel that's been treated to 460 isothermally. And from that, we see that the yield strength again has gone down to about 700 megapascals. Tensile strength has also gone down to around 1,000 or 950 megapascals, and the ductility keeps going up, right? We're getting more and more ductility from this, so that's about 15% elongation. And the hardness has also gone down to about 30 on the Rockwell C scale. And again, if we look at the fractured surfaces, we can see this again, and again we see kind of a change in shape, so it's no longer perfectly rectangular. We see kind of the cup and cone structure here. So again, the flat surface in the middle tends to denote a more brittle sample, and then some of these areas you can see in here represent the more ductile nature of it. So a mix of brittle and ductile, a higher percentage than the previous samples. All right, so now we're going to move into what we expect to be the perlite range. And so let's look at the 620 again. So again, here we held at 620 for about 2 hours, and we're predicting fine perlite plus ferrite. So what do our results show, and what does this look like? So these are the microstructures, again, from 2 different samples. And again, one thing you'll notice here is you'll see distinct regions. So in this case, we have a lighter region over here, over here as well, it's the shading looks a little different, but that part isn't important. But it's a lighter gray here, maybe almost like a bluish tint over here. But these are the ferrite that forms first, and then the darker regions that you see. So here, 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 and then also in these regions over here as well. This is the perlite, and so we expect to see ferrite, the lighter regions, plus fine perlite. So again, I mentioned the fine part. That means the spacing is very small. And so a lot of times, instead of being visually distinct layers, you might actually just see one color because the layers are so fine. Every once in a while, you can kind of see some differences, like over here, and over here as well. It looks like there's some layers, but sometimes with the fine perlite, unless the etching and so forth is really great, sometimes you don't see those layers. You just see kind of a light and a dark. But this is in fact fine perlite plus the ferrite that we see here. All right, so what is the properties of this then? So our mechanical properties taken from the engineering stress strain curve look like this. One thing to note is that you have this here. This is more of a yield point phenomenon, and this is indicative of perlitic or perlite-based steels. And this has, from the table that we see over here, strengths are even lower. So yield strength is 600, tensile strength 850, and the ductility goes up. So we're at about 20% elongation before fracture. So strength goes down, ductility goes up. We change to a yield point instead of the more gradual transition that we saw on the previous. And additionally, the hardness, the Rockwell C value is 24. So we're going down in hardness as well. And if we look at the tensile fracture surfaces, same thing. We see a continuation where we continue to see a change in shape here as more and more plastic deformation occurs. You might also notice the area is smaller because there's more and more necking. So we see that as well. So this sample is actually this on the same scale. It's actually smaller because we have more ductility, more reduction in area. All right, so 660. So in this case, again, this is where we would expect to see the medium perlite in this structure, and let's see what we actually get. So 660, again, we expect to see medium perlite and ferrite. So again, the light regions that you see in both these micrographs are ferrite, and the darker regions, which you can see some of the layering in these various regions, that layering is our medium perlite. So the layers are a little thicker than the previous sample. And so our strength again continues this trend. Strength goes down to 500 for yield, about 750 for tensile. The ductility continues to go up, so we're about 22 or so, and the hardness goes down, so we're at about 17. And so everything but the hardness was taken from our engineering stress strain over here. And again, we see the yield point. So perlite, we have this yield point, and again, substantial ductility that we see here. So from the fractured surface of the tensile sample, again, we see a change in shape, smaller than the original cross-sectional diameter. And the area here is not very flat, which indicates the ductility. So we see less and less of the brittle part, and it becomes a lot more, a lot higher changes of area here as it becomes more ductile. So we've got one more to look at, and that is the 700. So 700 isothermally transformed. Again, we heat up to 800 or above, hold there to get austenite. We quench down to 700. Here we're going to hold for around 2 hours, and we're going to get coarse perlite. And again, coarse perlite plus ferrite. So what do we get? So these are our microstructures for 700. And when you look at them, we still see the light regions, so the light grains. Those are ferrite. So ferrite in all of the perlites. And then for the perlite, the darker regions, you see more and more of the layers, right? So a lot of layers here, 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 And also on this other image, you see the layers, right? Because the layers are getting thicker and thicker, or coarser and coarser. And so you can usually see them better when you get up to these higher temperatures. So this is our coarse perlite, and then the lighter regions is ferrite. So here's our engineering stress strain curve. Again, we see the yield point phenomenon. We see a major drop in yield strength. We're down to 350. Same thing, tensile strength goes down to 700 or so, and the ductilities are highest. So we're at about 25% elongation at fracture. And the hardness, this is our lowest as well. So we got about 10 on the Rockwell scale. Again, if our experiment goes bad and we quench before we get perlite, this number shoots up. But in fact, the microstructure here, perlite, corresponds to the very low hardness that we see in this case. And again, our tensile fracture surface is again kind of not exactly rectangular because of the plastic deformation. This is not very flat from that ductile fracture, so we're not seeing as much of the brittle, and so this is less and less flat as we go along in these structures. So again, kind of thinking big picture, martensite has the highest hardness, the highest strengths, and the lowest ductility. Bainite's in the middle, so higher ductility, lower hardness, lower strength, and we go all the way up to perlite, where we get our lowest strength and hardness and strength, and then our ductility is the highest. So that kind of gives you the broad range of structures, and it all comes down to these different microstructures that we see. So the microstructure affects what these mechanical properties are, and so by understanding that and by looking at it, we can predict what the mechanical properties are going to be. So hopefully this video helped you understand how the microstructure can be changed by heat treatment, and specifically isothermal transformation for a 4140 steel. And how that influences the mechanical properties, and how we might use it in our applications that we talked about, like bicycle frames, automotive, aircraft parts. And so hopefully that tells you, hopefully that helps you understand the connection for this. And so hopefully I'll have some follow-up videos with different topics, some about 4140 steel, some about other mechanical properties and so forth. So subscribe to the channel if you like this.